Good afternoon. I'm Karen Nelson. I'm Dean of the School of Architecture at the Boston Architectural College. I want to let you know, 50 years ago this spring, the BAC initiated the Summer Academy for high school students to learn about urban planning, architecture, interior design, graphic design, and furniture. So we'll be celebrating 50 years of that in the coming months. I want to welcome everyone back to the afternoon portion of BAC Talks 2024. We had a very full morning of thought-provoking sessions that took place virtually, and now we're excited to host the remaining presentations on site at the college here in Cashier Hall and also with our audience online. We have a great lineup of speakers this afternoon coming from the 4 academic disciplines offered at the BAC. But before we get started, I want to thank our sponsors who helped make this event possible. They are 2D Planning, Ebrel Architecture and Design, Gannett Fleming, and Panetta and Associates. Thank you so much for your service. For those of you who would like to get HSW AIA CEU credit, please know that this lecture is approved for 1 learning unit, and the following lecture after this one is approved for half a learning unit, and there will be a sign-in sheet available in the hall, and if you'd like to do so through Zoom, please email ce@thebac.edu to get credit. Now to the main event. We're thrilled to have 2 luminaries joining us. The first is Isra Banks, BAC alumna and adjunct faculty for 6 years, as well as an architect at Gannett Fleming. Isra has 18 years of experience in mixed-use transportation and public housing projects. She focuses on affordable, sustainable design that enhances the quality of life with a commitment to energy efficiency, accessibility, and community engagement. Pardon me. The second is Huzefa Irfani, who is Director of Architecture at Gannett Fleming, with over 30 years in public sector projects. Huzefa has taught at the New York Institute of Technology, earned his Master of Architecture at the University of Pennsylvania, and is passionate about improving public spaces through design. Based in New York City, Huzefa Irfani leads nationwide teams in projects like renovating buildings and modernizing transit stations. They are here joining us to present resilience design in transit infrastructure, which will share innovative projects that address climate change challenges to infrastructure elements from the point of view of storm hardening and resiliency, as well as architecture and urbanism, with direct examples drawn from Superstorm Sandy. I will now pass it off to Isra and Huzefa. Thank you.
Go first.
Thank you very much. We're really excited to be here. Isra?
Well, yeah, thanks, Karen, and thanks to the BAC. It's a pleasure to be back here after, well, I'm here, sort of, but yeah, it's a pleasure to be on the alumni event. Our presentation is going to be about resiliency and resilience design in transit infrastructure. And I would like to see a show of hands of how many people use public transportation. I know I do. Huzefa does. And the MBTA moves around 3/4 million people every day. And it serves 4.7 million people in Massachusetts. And it has 153 stations around. And just for sake of comparison, the MTA in New York serves 4.6 million people. Rumor has it they're all Yankees. Speaking of sports, I would really be thrilled to see Bostonians support the MBTA as much as they support the Red Sox. I'm a big fan of the MBTA, and because there are lots of challenges that they deal with on daily basis to get people where they need to be. Number one is MBTA. Oh, the T is a legacy infrastructure. It's actually the first in the United States, first subway system in the United States. It was the part between Park Street and Boylston was established in 1897. And it was that part in Boylston has been designated as a National Historic Trademark. And similar with the Orange Line, Green Line, Blue Line, they were open to public by 1912. Another factor is a multi-model system where you can see from this illustration, there you have the commuter rail, you have the light rail, you have the heavy rail, you have buses, you have ferry. It's a lot to manage at the same time. You have fixed locations. Boston is a built city. You have it's built on low-lying land, which make it susceptible to flooding, and this is what we're going to talk about today. And it's inexpensive, which means that it's hard to get grants from the government, especially the federal transportation agency authority, because you cannot invest more than 30% of in renovation than the assets value. Another factor that makes improvements challenging is the lack of redundancy because of all the factors we said. There are not enough space. You cannot move trains back and forth. You have to stop service to make the improvements. So most of the work happens at night.
I think
Now,
one of the things, I'm sorry, that the uniqueness of the MBTA is, in a sense, not unique to the T. Most of the transit infrastructure we have in the United States is old. I mean, I don't think I'm surprising anyone by saying that. And the requirements of today are very difficult to retrofit on what was designed, 100 years ago. So, I mean, this is a unique challenge, I think, for engineering disciplines, architects, everyone, in order to find solutions that really address some of our most needed challenges.
So now that we have established the relationship between transportation, people, and somehow sports, let's talk about how climate change is the biggest challenge, or one of the biggest challenge that faces the transportation. The MBTA has identified components of vulnerability in 5 items: sea level rise, change in precipitation. That's what we've seen yesterday. It's hail, snow, rain, sleet, all of it. No, anything coming from the sky. Extreme heat, extreme wind, and snow and ice. And next slide. Coastal flooding. That's what you see. We're going to talk about later on the Long Wharf Aquarium Station. You see that picture on the left. So this is probably property of Boston Development Agency, but as you see, the flooding affects the MBTA Aquarium Station. So there has to be this collaboration, and they had to reinforce the seawall and all that. On the left side, you see the picture speaks for itself, but you see that the snow has stalled the red line in 2015. Now, extreme wind can also affect the service, and if it falls on these catenary cables, it might cause a lot of damage. And actually, this what happened in Hurricane Sandy in 2012. There was a lot of damage on the Green Line. On the left, you see this is Columbia Junction, low-lying land with flooding also disturbs the service and causes a lot of damage. Heat, high temperatures. So one thing, it might cause buckling because of steel tracks. Another thing is comm rooms. So you see the signals for the subway or commuter rail, and these signals are very important that you cannot have service without them. And if these communication rooms, which have the equipment, we call them BACs, if they get damaged, then they're not repairable. You will lose signal. It's a lot of money. It has to be repaired. So we work, we have to make sure there's redundancy.
And we're doing some work currently with the T in order to fortify the communications rooms right now. So it's, again, there's a lot of things that happen in the background that allow our public transit to work.
So MBTA have done a lot of work to mitigate all these dangers. They did a climate change risk assessment, and you can see from this exhibit. Next slide, please. Yeah. You can see from this exhibit, they have identified the assets that requires and studied for each asset what is the climate change risk on it, and we call it exposure, how climate change is going to affect this. And also another factor is it's the asset sensitivity. So so let's say how much flood water is coming in, how much heat, and then how sensitive it is, the function, the population group that's going to be affected. And by multiplying these two factors, they came up with a score from 0 to 15 to identify how to mitigate. And then you see in the schedule, sea level rise is very high, it's high risk, and it has a high vulnerability score, temperature as well, and then the rest of it falls into moderate and low. But you see sea level water is one of the main issues, which lead us to flooding. If you see this schedule in the past 100 years, from 1920 to 2020, sea level went up by 6 inches. In the next 100 years, we think that sea level is going up by 2.4 to 7. Actually, there are spots where it's going to go above 10 feet. You see this map. The green area is the 2.4 to 7. The blue area is around 10 feet. The areas where it's more dangerous, where it's more vulnerable, there are many, especially like communication rooms, fan rooms, because I was going to talk extensively about fan rooms for the subways, and communication rooms as well, but also the elevators, and any, like, one thing they can disrupt service, and another thing they can cause like multi-million damages if they get submerged by water. Next slide, please. Another factor is, next slide. Another factor is human health. The T is very concerned about human health for the people, the riders and their employees, because seawater contains pathogens and algae, and another factor, it's also causes rust and corrosion to the tracks and equipment. Next slide, please. Okay, now that we have established water as our #1 threat rather than extraterrestrials, surprisingly, let's talk about what the MBTA plan is. They start utilizing real-time storm data mapping, you see in the map, and connect it with the weather, the national weather maps, and see up-to-date map, so they can mitigate the risks in time. They also partnered with MIT to come up with a study to work on this. So the MIT study, it went through 3 three aspects. They looked back at how flooding has affected subways in the past. You see the picture in 1966 where people are going out through a boat. You see the man in the yellow jacket. We're going to revisit that Fenway Park. And that's the same place in 2021 under construction. They also they used a climate risk vulnerability assessment tool. That tool was developed by Southern California Association of Government that specialize in transit risk assessments. And they did a system-wise flood model cost estimate, so they can mitigate as based on like, if this is going to affect us, what is the risks, how much money we're going to spend on it, and like how much money we need to fix it or mitigate it before it happens. That's also from the study. The modeling shows, and I know architects love sections, shows you shows you the red line you see in 100 years. Broadway and Andrew both submerged in water. You see the orange line have some water. Also the blue line heavily affected. We're going to revisit that blue line. If you notice the link 10 in the middle of the picture, that channel between the airport and Boston is going to have 15 feet water depth. So this is one of the highest. And the picture shows you the blue is like about 3 to 4 feet. The dark blue goes above 10 feet. Again, that's probably we've mentioned that before. So what is the T doing about it? They're doing a lot of work. They've done a lot of flood doors. These aluminum panels you see on the right side of the screen, and water pumps to pump out the water. Also, the Boston Planning and Development Agency been helping to fortify the Long Wharf Island. If you remember, we saw that picture of the water coming in to the aquarium station. So there are multiple factors that goes into helping the T. It's not just one agency's work. Also, the Army Corps of Engineers proposed a $52 billion to protect New York, and they're planning to do the same for Boston. Next slide, please. Oh, remember the picture of the man in the yellow jacket? It was flooded in 1996. So the part of the studies, they realized that this is one of the areas where it's susceptible to flooding. They started building these flood gateways, retractable gateways that would protect the tunnel from water. Same thing with the aquarium station. Flood doors, panels, cameras to make sure that they know what's happening real time. With that, I hand it out to Josefa to talk about a very exciting project that he has led in New York City.
Thank you, Isra. So we've armed you with a lot of facts and figures about what's happening with the climate. And it's probably, you're probably wondering, what do architects have to do with all this, and how do we address it? What is it we can do? I think part of it is obviously an understanding of what the problems are and trying to see, and this really is one of those cases where it's not purely an architectural problem. There are engineering issues associated with all of this, and trying to find this intersection between architecture and engineering is sort of key to addressing this problem. So I'm going to ask you to go to the next slide. So Isra's done a fantastic job of just sort of putting the overall problem in the Boston perspective, but let's take one step back even further and look at the timeline of storms that have started to happen in the United States. In 2005, Hurricane Katrina hit the New Orleans area. It was a tremendously significant storm for the area, tremendous rebuilding, tremendous cost, lots of lives lost. In 2017 alone, 3 storms across the United States hit. And of course, the key storm that hit the New York metro area was Hurricane Sandy. And that project really triggered the project I'm going to show in the upcoming slides. So the damage to New York, 17% of New York City was underwater. And floodwaters in certain areas, Staten Island in particular, reached 14 feet. Because I work on a lot of transit stations, Lower Manhattan was completely flooded. There's a tunnel that connects Lower Manhattan to Brooklyn that was completely underwater. And now we're talking about salt water. So this is all highly corrosive stuff. Airports were closed. All the regional transit lines were closed. And if we jump to the MTA in particular, $4.7 billion with a B of damage to the system itself. In order to sort of fix what happened, the cost was $8 billion. Next slide. So all the things that are happening since these storms are happening, I mean, the collaboration that the T is doing with MIT, we are all learning, okay? And when Sandy hit, that was like an immediate, like, eye-opening, what do? We have to figure something out. And in partnership with the MTA, and this is sort of what's key to all of this, is trying to understand what are the vulnerabilities, what are the weak spots of the system. And these are things that we as designers don't always know without having a direct input from our partners or clients. So we had to consider the normal stuff, static load, the hydrostatic pressure. They also considered flowing water as a potential design parameter. And then this kind of took me by surprise, but like, it's not just, oh, the water is going to be this high, so my flood barrier has to be a little bit higher. It's impact loads on the actual barrier that you're creating. So they were concerned about waves and things, objects hitting it. And one thing I want to mention real quick is that, like, so slosh maps. I love the term slosh, because so I had to write it on a Post-it because it's kind of the Yiddish words, they sound like what they are. So it stands for sea, lake, overland surges from hurricanes. And but what's important to know about it is that it was a more reliable source of data than FEMA was at the time. And FEMA maps were not kept up to date. As probably everyone knows, FEMA is generally used by insurance companies to determine, flood hazard. But in fact, when we started designing, we couldn't rely on that information. So we were looking for other sources. And again, as I mentioned, seems like MIT and other institutions are now getting involved to even kind of bolster the flood data that's being used for design. There are American Society of Civil Engineering standards that were used, ASCE. And again, I mentioned the load factors that were designed or used for the design. Next slide. So the New York City system, again, not different from any other major metropolitan transportation system, contains stations, which is the part that everybody knows. But behind all that, there are ventilation plants, there are substations, there are comm rooms, communication rooms, there are pumps. And one of the things that's unique to any coastal city is how much water is actually in the system that needs to be pumped out. And for New York City in particular, 700 pumps operate the system, removing 13 million gallons of water per day. And this is a normal operation. So when a storm hits, this is a catastrophic thing for the system. And then building generators. A lot of our transit system, Isra mentioned that redundancy is a problem. It's, for any project that goes on in transit today, the eye is always towards redundancy. If this fails, what do? I have to have something else. So, that was part of whatever we did, had to have redundant features in the design. And then one key thing to note is like we always think of flooding as an above grade problem, but it is a below grade problem. So anything that penetrates your building or water gets it one way or another, it gets it. And so part of our design issue or problem had to deal with any kind of penetration below grade. Next slide. So this is an image of the fan plant that I'm going to talk about in a moment. And it was located in Long Island City, Queens. It was a fan plant that that connected between the East River and Manhattan, or the East River, Manhattan and Queens, but this was on the Queens side. Let's say the green line that you see over there is actually grade level. Hurricane Sandy is the orange line, so it's about 1.7 feet. And then, you know, the various design parameters that we considered category 1, category 2 are represented by the dark blue and purple lines. So they really took sort of the long view in terms of this is what Sandy did, but like what's going to happen in the future. And I'll talk a little bit more about some of the vulnerabilities. Very quickly in the next slide, I'm going to show you what our design solution looked like, but I'm just going to give you a teaser and then go right into our next slide. So like I said, it's located in Long Island City, Queens. What does a fan plant do? They're not occupied buildings typically. This particular fan plant and most fan plants, because it's connecting an underground tunnel, there's a piston effect created by the trains, so it needs to release air in case there's an emergency and there's a fire in the tunnel. It evacuates the smoke from the tunnel, so they have these massive fans that exhaust the air, and these fan plants are not on one side or the other. They're typically on both sides of a tunnel. Most often people have seen these ventilators are kind of all over the place. So you see them on your sidewalks. Everybody remembers the Marilyn Monroe scene. So this is sort of the function of what they do. The site itself is a rapidly urbanizing part of Long Island City, Queens. You know, oftentimes these fan plants are not things you distinguish in the urban landscape very often. Next slide. So this is the way we found it. The building itself was built sometime around the 1920s with various additions taking place. It looked kind of like a bunker, not very attractive. It did surprise me that the existing building did not have that sort of flavor of 1920s buildings where there was a little bit more pride in sort of the architecture of even, you know, these kind of utilitarian buildings. But, you know, what you see at the back is the actual fan plant. You might be able to distinguish a little bit that the fan plant is not orthogonal with the street grid. It is actually aligned with the underground tunnel or tube below. And in front, the gray box is a transformer equipment that, again, in part of providing power to the pumps, it's kind of all these functional things, just these guts of the building just spilling out, and surrounded by a razor ribbon fence. So not terribly attractive, let's say.
And also, if you look closely, you can find graffiti. I've been telling Josefa it looks like a place to attract criminal activity. And I'm so glad they did a new design that solved these problems.
So next slide, please. So the vulnerabilities, I showed you the slide that had the various lines that depicted where the flood went, but you can see pretty clearly from the existing images that the red louvers around the building were pretty low to the ground, so floodwaters got in to the building and affected the operation of the plant. The middle picture shows a big garage door, and that was another vulnerability because the garage door is not designed to resist the flood. But the reason for the door is that that equipment needs to be maintained or replaced from time to time, so they need to bring this large equipment in. And these louvers actually surround the back, and so 3 sides of the building have this louver. One sort of secondary function of this particular fan plant, not true of all of them, is that it's an escape route. So in case there's an emergency in the tunnel, there's this tall stair that the public might have to use in order to get out of the out onto grade. Next slide, please. So as I mentioned, the louvers are below. These are just straightforward elevations that show that this DFE stands for design flood elevation. So they're below what we consider the design flood elevation. Transformers were at grade, the gray boxes out front. As I mentioned, those gray boxes had utility feeds that go underground, and there's other communication rooms as well that were underground that were issues. Next slide. So our structural engineers are really smart, and they come up with great diagrams that explain how flood loads work. I think anybody who's taken a structural course has seen a diagram like this. So they had to really come up with the loading factors that addressed all of the things I mentioned before, the slosh map, the impact loads on the walls. And so this is what the diagram basically shows. The other part of the design also had to do with near-term and long-term. So the event happened 10 years ago, but it was going to take 2 years or so to actually implement this stuff. So the MTA was looking for near-term solutions that would be deployable. And so they could go out, so similar to what the T did, where they brought out the flood logs or the barriers, they would be put up around in case something happened before we actually built the permanent thing. And the long-term solution was what's called a passive solution. So what that means is nobody has to do anything except check it, make sure every now and then that it still works, but it's in place. There's not much to be done. Next slide, please. As I mentioned, the fan plant is non-orthogonal to the site, so that created unique design problems, because we have a pinch point, as you can see from the near corner, and then the far corner that you can't see so well from this rendering, created issues for construction access. How do you get to the back of the site in order to kind of deal with all the retrofits that we have in mind? You're pinched at the front because of these transformers that are out there, so lots of conditions. Another part had to do with the fact that the MTA, because this is an operating system, they couldn't take this thing offline. So anything we did had to be done in a way that didn't shut down the service of the fan plant. So next slide. So the issue, so here you see our fantastic structural diagram superimposed on the building. Because the building was designed in the 20s, it was not designed for flood load. It never anticipated sea level rise like what we're experiencing today. So we had to find a way to retrofit the building to accommodate or take these loads. Another constraining factor was that there are tunnels that operate the subway below. So we could not do any deep foundations. So that was another constraint. So I'm going to go to the next slide. So our smart engineers came up with this idea of trying to use the existing slabs as a diaphragm to resist the flood loads. So we built an exoskeleton steel frame and pinned it to the ground floor and roof slab and transferred the loads that way. Obviously, in doing this, we are enclosing the ground floor or the lower level of the building. So we needed to build an addition on top. So that leads to one thing leads to another. So next slide, please. So this is our exoskeleton in plan, our shallow foundation detail at the left. So as I mentioned, underground penetrations are a big deal. So now we're building this fantastic flood wall around the building, but we're still concerned about how this whole thing hugs the existing building so water doesn't come in underneath. So water stops had to be designed. The pinch points at the corners had to be dealt with because we're building outboard of the existing building. We were lucky in the sense that the MTA is a self-governing authority, so zoning codes or restrictions like that were kind of waived as long as we could demonstrate there was no risk to other buildings in the area. Next slide, please. The addition at the top necessitated, a lateral shear wall system, so we had to install additional structural retrofits in order to make sure that, the thing we're adding on top did not, the addition did not somehow compromise the structural integrity of the existing building. Next slide. So many transit agencies, and I don't mean this as a criticism, they over-design. And the transformer pad, we were lucky in the sense that we needed to enclose that pad. And even where that's located, there were major DC feeders, direct current feeders running underneath this slab. But it was so robust that it allowed us to anchor and build an enclosure around the transformers and replace the transformers, and as well as build a second story above it. So in some ways, I think we're really lucky that our transit agencies decide to overbuild in a sense, because this kind of allows us to make some of these retrofits a little bit more easily than would be otherwise the case. Next slide, please. So the section shows the blue area is sort of the existing fan plant on the right. There were critical spaces shown in the green that you see up on the slide up there. And then the lighter green are the additions that we built on top. So one of the kind of unusual benefits or unintended benefits, by raising the louvers, these fans for the fan plant are actually oriented vertically inside the shaft. So air movement is more naturally conducted up through the addition and up through the higher louvers. And I think overall, there was, you noticed from the existing condition photos that the louvers were red. There was complaints from the neighborhood at the time before this retrofit happened that they were too loud. They have to test the fans every now and then. They're very loud. So there was all kinds of acoustical baffles that were part of it. So in any case, part of the solution alleviated another problem, which kind of is a accessory benefit. Next slide. So, okay, now I'm going to talk about the architecture, finally, after all this stuff. So the building, this is the final solution. We had to build, as I mentioned, an addition on top. So you see the building in the front is where the transformers used to be. The black granite cladding is the base, which is the fortified flood wall of the fan plant. The rest of it is basically a perforated metal screen wall. The great thing about these buildings, at least from an architectural point of view, is that they're not occupied in some ways, which is good and bad. I like occupied buildings, nothing against it, but it allows a certain freedom that we wouldn't have had otherwise. So we can express some of the functional characteristics of the building. So the chosen cladding above was a perforated metal, giving it a certain effect. Next
No
slide.
graffiti there.
No graffiti. So you can see from the picture on the right, the perforated cladding is an exoskeleton. We really wanted to make a statement out of the fact that this is an addition. This is kind of built out, so it gave it this kind of gauzy feel. You could kind of see through the corners. The louvers on top, as you can see, the new ventilation, it gave it a different monumentality. I argue, like with the building previously off the grid, the new building or the sort of addition starts to reorient the building back to the grid at the street level. So there's a negotiation happening there. Next slide. Some of the additional functions that we had to put above the transformers had new feeds going into the existing building. So we didn't want to create any more underground penetrations, creating new problems. So we created what's this cable bridge. The cable bridge actually becomes a canopy for the new entrance to the fan plant. We tried to make use of some of these things in architectural ways wherever possible. The figure at the right, so you remember the large garage door that was opening up. So that was a real challenge. We had to work with vendors who designed flood doors in order to come up with something that was large enough that could take the flood loading. So these guys had to test all of their products. It was all a beta test, to get this to make sure it would function as designed before it actually arrived on site. Next slide. So the slide at the right is one of my favorites, just because, again, it's a project that really speaks about the city in many respects. And it's a project that, as a passive building from the point of view, people don't generally notice these things in the infrastructure or in the landscape of urban landscape, but it's an important function. And, to me, it was a kind of a pleasure to sort of work on something that people don't typically go inside. And so I'm going to ask you to advance to the next slide, a view from the back. And As I understand it, the yellow building to the left of the fan plant is actually an art storage warehouse, top secret stuff. We were never allowed to access. I think armed guards greeted us at the entrance. This is, you cannot go in there, but because of the arts, whatever we built next to it, they were particularly concerned about any kind of vibration. So there was a unintended additional challenge there. I just want to say, like, when I went to architecture school, transportation was not really talked about as an area for that architects influence. To my pleasant surprise, there's a lot we can do as architects to influence these public spaces. They're sometimes, not always seen as the glamorous projects that architects get, but there's so much we can contribute. There's so much between the interaction and intersection between architecture and engineering in these type of spaces and buildings. So I would really, hope some of you might, through this presentation, be a little bit inspired to look at these buildings in a different way.
I want to add special thanks to Hannah Lyons Galante from the MBTA. She's Deputy Director of Resiliency for helping out with this presentation. And thank you. Probably if there are any questions.
Any questions in the hall? If there are none, I'll I have one comment. Can I be heard if I go to the podium? Don't go far.
Nope.
This morning, the very first presentation at 8 a.m., we were looking at Iceland.
Okay.
And we all know that Iceland has geothermal power just for digging underground.
Right.
And very often when I walk around New York and Boston and see these infrastructural buildings, I think of these cities having their own infrastructural power that's getting lost into the atmosphere. So all that heat that's being removed from the tunnels, this gorgeous new building. Is there any thought to giving it over to a nearby building that needs that warmth or cool over time?
Yeah, I think there's,
question.
it's there's a lot. I mean, really, honestly, to be done with all of these buildings, and there's a lot of thinking that could go into how we can make kind of other benefits happen when we do these projects. And I think we were able to do some of that with this project, but the thing you're bringing up is fantastic. I think, unfortunately, there's certain funding limitations that prevent them from going on. But I think this is where, like, an academic institution, in my mind, can really contribute to the way, people think about these projects. You could start to say, like, what other benefits? I remember when I was in college, there was someone working on thesis to address homelessness, which unsurprisingly or unfortunately hasn't gone away. But some people were looking at subway vents because of so much heat coming out as being temporary places where, people can get some warmth and find a place to sort of spend the night, let's say. I mean, it's not pretty, not, great that would be a solution, but just I was kind of struck by the ancillary benefit potentially of something like what you're talking